Hey, everybody. Welcome to the last talk of the afternoon session. Let's give a round of applause for Christophe Pettus.
Hi, everyone. Hi, everyone. My name is Christophe Pettus. I'm the CEO of PostgreSQL Experts. We are a small Postgres consultancy based in sunny Alameda, California. This is my technical blog, thebuild.com. That's where the slides will be, the #1 question everyone asks. And my Twitter handle is XOF, and there's my email address. Spell it just like it sounds. There's so much stuff that we could potentially cover in this. Django 1.7 introduced native migrations, and 1.8 introduced and 1.9 extended Django.contrib.postgres, which is mostly what we'll be talking about this afternoon. A lot of features, but the first thing I want is everyone take a moment to thank Mark Tamlin, who deserves the praise of a grateful nation for implementing most of these features. He did wonderful, wonderful work on this. So the first thing I'm going to talk about is native migrations. Which the first thing you'll say is, well, wait, those aren't Postgres specific. Why are you talking about them? And the reason I want to just go over them quickly is because they're an enabler for a lot of the other stuff we're going to be talking about. So I just want to get everyone up to speed in case. And 1.7 migrations are just amazing. They're really, really nice. So thanks to Andrew Godwin, who implemented those. So the quick overview is migrations are used to move the database from one version of the schema to another. And they're built around this idea of a sequence of operations. Each operation moves the database either backwards or forwards through its schema migration timeline. So if you've modified the model, the migration subsystem analyzes it, decides what SQL needs to be applied to the database, generates an operation to do that, and lets you apply it. There are a lot of operations, but we're going to talk about two in particular, which aren't automatically generated, but which are extremely useful, which are RunSQL and CreateExtension. The RunSQL extension applies raw SQL directly to the database. The whole thing, and at this point you might be thinking, isn't that exactly why we had migration, so we didn't have to do that? And the answer is yes, but to take full advantage of some of these features, you do still have to send some raw SQL down. Specifically, a lot of the new stuff, to create indexes for it, you're going to need to write a little bit of SQL. That's okay. It won't hurt. It doesn't bite. Similarly, to get a couple of other things working, you're going to, I'm not used to that, to the closed captioning. Similarly, to get other things working, you'll need CreateExtension. For example, if you're using hstore, who's using hstore in production? Still a lot of people. So to do that, you need to create the hstore extension in your Postgres database, and the CreateExtension command does that, and the CreateExtension migration operation will do that for you. One problem with hstore is it does have a query to every connection to the database, which is kind of annoying. Okay, now to the good stuff. The Postgres extensions in 1.8 and 1.9 introduced array field, range field, hstore field, and JSON field. Array fields, now arrays are first-class types in Postgres. You can have a single column that is an array. This was an underused feature in Postgres, especially in the Django world, because there was no real easy way of doing that. No excuse anymore. Now we have them as first-class fields. An array field lets you use them directly. They map onto Python lists, and but unlike Python lists, PostgreSQL arrays are of homogeneous type. So if you have an array of floats, you can't stick a character string in the middle of it, sorry. They're homogeneous types, and they're good old-fashioned Fortran-style orthogonal arrays. So you have a 12 by 17 array. You don't have a list of lists, so just kind of get used to that if you use these. In addition to now having array fields, we have operators, the operations you can do in query sets for arrays, like the __ contains, which matches if the array field on the left contains all the entries on the right. So for example, that contains that, but that does not contain that. And the order isn't important in contains. So that's kind of cool. So you can do queries on these array fields. Contained by works the other direction. So that is not contained by that, and that is not contained by that, but that is contained by that. So it's the reverse. Order's still not important. We get overlaps. Matches the array on the left, contains any of the entries. So A, B, C, D overlaps those, but does not overlap D. And length, which unlike the others which query on array values, this one returns an integer. So you can query for arrays of length 2. Note that this is always going to, unless you've created an index specifically to accelerate this will always do a full table scan because they have to walk up, pick each array, determine the length, and put it back down again. So be judicious with it. You can also now query the first field of an index, or of an array, excuse me. So find everything whose first element is A. If there is no 0, for example, it's a 0-length array, it doesn't raise an error, it just doesn't match, returns false. One of the unfortunate things about this syntax is you can't specify the index programmatically unless you build it yourself using quargs or something like that, so it's hardwired in there. You can also do slices, compare things on 0 from where entries 0 to 1 are A, B, and do contains on those if you want. Now, so doing all of these is great, but you're stuck with having to do a full table scan every time you use them. And so you just say, okay, well, I'm going to do what every Django programmer does, which is set a bunch of stuff to db index equals true because I think I might query on it later, and you're done, right? Wrong. It creates a B-tree index, which is pretty useless for an array, and pretty much any non-scalar type, a B-tree index is not what you want. You want a different kind of index type to accelerate these queries. So let's talk a little bit about Postgres indexing. Postgres supports multiple types of indexes. In fact, Postgres has a whole mechanism called access methods for plugging in new types of indexes. And some of the things that plug into it using access methods, like gist indexes, are themselves frameworks. So it gets really complicated really fast. But we'll make it a little bit simpler. Most people are familiar with B-tree indexes, with or without a little hyphen between B and tree, because that's what you get when you specify db index equals true. That's the default type, unless you specify something else. B-tree indexes are great. They're compact and they're fast and they provide total ordering, but they only really mean anything on totally ordered types. And what totally ordered type means that the standard comparison operators greater than, equal, or less than are meaningful for them. But think about a point or a range. What does it mean for one point to be greater than or less than something else? You could sort of concoct semantics for that, say, well, we'll compare the first value and the second value. But semantically, that doesn't really mean anything. They're just points in space. But they do have other operators. For example, a point in a rectangle has inclusion, is this point inside of it. Ranges do these ranges overlap? And to accelerate those kinds of operations, we have different kinds of indexes. Specifically, we have gist and gin indexes. So gin indexes are good for types that contain keys and values, like arrays, like hstore, like JSON, where you have a key and that key maps to a value. Gist is generally used for types that partition a mathematical space, like points and ranges. Like a rectangle, partitions of space. There's things inside the rectangle, there are things outside the rectangle. And for stuff like that, ranges similarly, there are things in the range, things outside of the range. And for those, you generally want a gist index. The nice part about them is once you've created them, they just work. You don't have to say, do this query, and oh, by the way, use this gist index. Postgres is smart enough to know that for you. So let's talk, since we talked about array fields, let's talk about indexing array fields. Arrays support gin indexes, which is short for generalized. The claim is it's short for generalized inverted index. However, the same crew that came up with gin indexes also came up with vodka and rum indexes. So I wonder if this acronym is actually what they had in mind, but whatever. If you have a gin index, that'll accelerate contains by and overlaps on those fields. But it doesn't help with links or slice operations. Sorry. To create one of these, you need a slightly different syntax, which is there's the table name, which, app_model in Django terminology, using gin and the field. And that creates a gin index on that field. Gin indexes can be large, especially if there's a lot of data in the underlying tables. If these are big tables, the gin indexes can be pretty large. They're also kind of not free to update. Postgres 9.5 and 9.4, however, have some optimizations in this regard, so this isn't as big a deal as it used to be. But just keep in mind that compared to a B tree, these could be both a time and a performance size hit. So don't create one unless you need it. There is this unfortunate tendency in Django because saying db index equals true is so easy, people create lots of indexes they don't really need. Small tables in particular don't really generally need these. If the table can easily fit in memory, don't bother with an index on it. So if you need to index the length operator, you can create what's called a functional or an expression index in Postgres, which is an index on the array length operation itself. And if you're doing lots of stuff on a particular slice, you can index the slice. Note, remember, Postgres arrays are 1-based, unlike Python lists, which are 0-based, because it was the 90s. It made sense at the time. OK, so now that we've got array fields, why would you use them? First of all, well, maybe the underlying data is actually an array. For example, it's a sequence of points, a sequence of samples that's coming in from a sensor or something like that. Arrays are often a really nice replacement for a many-to-many table. The classic example of this is in the social media issue where you have 1 million users and 1 billion things, and you're trying to keep track of what likes what, of who likes what. Having a many-to-many table, if you just do the multiplication in your head, you realize that's a lot of zeros for the size of that many-to-many table. It might be better to store things as an array of, I like the following things, and these following things are liked by these people. So that's a possible use for them. You can also use this as a denormalization to store the results of an expensive query. So the underlying truth may be in different tables, but you keep an array field up to date because it's the pickled result of a query. Do proceed with caution there, because going crazy with denormalization can be a problem, but a little bit of strategic denormalization is not a bad thing. See, someone who calls themselves a DB expert just told you that. OK, and that's arrays. hstore. So for those not familiar with it, hstore is a semi-built-in hash data store. It's like a dict in Python, but it can only take strings as keys and values. So it's a single-level object. That sounds pretty unexciting, doesn't it? Oh well. But it was all we had for a long time. Before we got JSON directly in Postgres, this was it for doing that kind of unstructured data. So we learned to love it. One of the things about hstore is it doesn't ship as part of the core in Postgres. You have to add it as an extension. It does ship in the contrib modules, so usually it's available on your system, but you have to specifically say CreateExtension hstore to get it to work in your database. Fortunately, Django contrib Postgres comes with an hstore extension migration operator to install it for you, so that part's good. One thing to be aware of is if you are using the basic unaltered Django connection model where every single web cycle connects to the database, please don't do this anymore, but that is the default. Every one of those connections will now have another query added to it because it has to get the object ID of the hstore extension every time. If this does not, it's usually not a big deal, but just be aware of it. On the Python side, it's represented as a dict. The keys and values have to be strings, like we said. And it's automatically translated to and from the database encoding if you have one of those really unfortunate databases that isn't in UTF-8 encoding. It should be in UTF-8 encoding. So you can do you have a lot of the same kinds of queries for hstore. You get contains and contained by, where both the keys and the values must match. You have has key, which matches a field containing a particular key, and has keys, which does the same thing only with a list. And has any keys to do the OR style operation to match a field entry that has any of the keys. So you also have there's also a transform which returns the keys, so you can say, get me all the keys and then do an overlaps on it that says, okay, what I'm looking for is any record that has this hstore field and that has keys A and B in it. And values does the same for the values side. You can also, if you're using hstore and you need to index it, you can index it with a gin index as well. And that does contains, has keys, but it doesn't help for contained by. But they're just the reverse of each other, so it's not that big a deal. So why would you use an hstore field? Well, it's great for storing really rare attributes. One example is, suppose you're shipping a package system, like a storefront system or something like that, and you want the user to be able to create their own attributes, like color for garments and things like that. But you don't want to go and modify the schema every time, and in Django, that's a pain to do anyway. So you could create an hstore field that has those relatively rare attributes in it. One thing to be aware of, though, is if you're using multiple fields that are so if you're have a field that's null 95% of the time, consider moving it to an hstore field and getting rid of the column. One thing to remember, though, is that null fields take 0 space in PostgreSQL. They don't actually take any space on disk. So you're not wasting space by having a column that's null. So, or user-defined attributes, where the user can create attributes on things at runtime. The reality is, though, if you're starting something from new, you're probably going to be using JSON instead of hstore. And we'll just talk about JSON in a bit. But if you're still on Django 1.8, it didn't have a JSON type, so if you need something like this right away, use hstore or upgrade to 1.9, which you should do anyway. Or, of course, you have an existing database with hstore, and now you want to use it in Django nicely. Okay, Postgres semi-recently introduced range types as part of the standard type suite, which are really nice. They span a range of a scalar type. So, for example, the range 1.8 includes those. You can also have exclusive bounds, which are for continuous types, like floats are important. So that excludes 8. Because it does include the end. Default, this is the default, is that it includes the first point but does not include the last point in the range. You can also omit a bound to indicate all values less than or greater than. So whether that is mathematical infinity or not, I don't know because I'm the world's worst mathematician, but you get the idea. Also, some types, like dates in particular, have a special infinity value. PsychoPG2 includes a range type as part of, PsychoPG2 is the standard interface library that pretty much everybody uses to talk to Postgres. It has a range type that includes all that stuff for you. So that's how these are represented inside of Python. Out of the box, 1.8 supports integer range and big integer range, so 32 and 64-bit integers, floating point ranges, date time ranges, and date ranges. So those are built-in fields and types in Django 1.8. You can do contains, contained by, and overlap pretty much the way you'd expect them to. We also get a fully less than and fully greater than if they are completely disjoint one way or the other, greater than or less than each other. And adjacent to is true if the ranges exactly butt up against each other. So you could merge them into a single range correctly. Yeah. And then not less than, true if the field does not contain any points less than the value, greater than kind of what you expect. So if you want to index these guys, this is where you use a gist index. The gist syntax looks just like the gin index, except you say gist there. For anyone curious, gist stands for Generalized Index Storage Technique. Everything I've talked about is accelerated by a gist index, so woo, that's very nice. Now, what would you do with this stuff in Postgres? Well, here's a really hard problem. Let's say you're building a hotel reservation system, and you say, don't allow 2 bookings to be inserted in the database for the same room where the dates overlap. And you want this to be a constraint in the database. You never want data like this to go into the system. So you don't want to do a query, check, and then return because there's a race condition there. Someone could jump in and do a bad booking. The problem is there's no way of expressing this with a unique constraint. because overlap isn't, because two ranges can overlap and still not compare, be identical for comparison purposes. And unique is only equality. Fortunately, Postgres, relatively pretty much all recent versions of Postgres, have a way of handling this, which is called constraint exclusion. Constraint exclusion is a generalization of the idea of unique indexes, which says instead of just saying don't allow two equal indexes, but based on this set of comparison operators rather than just equality into the table. And these comparisons can be any Boolean comparisons that can be ANDed together, as long as they're supported by indexes. So there's one catch, is that it all has to be in one single index, which means if range type support a gist index, that index has to be a gist index. But the problem is one of the constraints was on room number, or room code, whatever we want to call it. But by default, these don't support gist indexing. So it's like, oh, well, I just told you this great feature, and now you can't use it, right? Well, there is a way of using it. There's a module that you can install in Postgres called btree-gist, which allows you to create gist indexes on simple scalar types. It's an extension. It's part of contrib, so you get it as part of the standard source distribution. It has to be installed in the database, but again, it ships with Postgres. So you can use the CreateExtension migration operator to stick it in your database. So let's see how we'd actually do this. We import the usual stuff, and here's our schema. Very sophisticated. Here's the room, here's the dates. Okay. And here's what the table then looks like. It created the usual, because Django always creates this, the room and the date, and the primary key on it. Okay, that's boring. So then we create btree-gist, and then we create this really super fancy exclusion constraint, where we say, okay, exclude using gist. The using gist is just like the using gist in an index creation. Anything where the room is equal and the dates overlap. Which means we're saying don't allow two records where the rooms are equal and the dates to overlap to be inserted into this database. And here's what happens. So we create a date range and insert it, a booking and insert it, and then we created a different booking that doesn't overlap. See, they checked out, they checked in. Hopefully we have time to clean the room. Then we created a booking that directly overlaps that, but it's a different room, so Postgres has no trouble with that. Then we try and create one that they check in, but they're checking in at an overlapping date. And bang, we get a constraint violation. Cool. So we've solved this problem, this very hard problem. So using range fields. You use range fields to represent ranges. You probably could have guessed that. Specifically, they're more natural than the high-low pair, which we have always used to represent ranges in the database as two separate fields. Specifically, we get better database integrity, and we get a lot more interesting operations here. OK, JSON. Everyone uses JSON all the time for everything now. JSON was introduced in 1.9, in Django 1.9. And these are fields that support arbitrary JSON structures. They're stored as the JSONB type in Postgres. They support contains and contained by, where, again, the keys and the values have to match, just like hstore. Has key matches fields containing a particular key, and has keys, blah, blah, blah. You probably remember this from hstore. So these work just the way they did on hstore. These all work against the top level of the object, of the JSON structure. They don't peer into nested keys. So it's all the top level. You can do path type queries. So you can say, find all the dogs, so it looks for a key owner, which has whose value is an object, which has a key name, which corresponds to Bob. And you can use array indexes if the underlying JSON value is an array. Now, Postgres actually supports two different types of JSON field, JSON and JSONB. JSON supports the raw text of the blob, white space and all, while JSONB is a compact and indexable representation, sort of like BSON, only much better. So why would you ever use this JSON type? It's faster to insert because it doesn't have to compress the data. unless you have a really pathological JSON blob with tons and tons of white space. JSON also allows for these two highly dubious features that unfortunately some JSON APIs require, which are duplicate object keys at the same level in the object or stable object key order. These are not actually, there's nothing in the JSON spec says this is not required behavior. And in fact, most implementations of JSON libraries don't allow this, but some APIs do. And so we allow you to do this in JSON, but not in JSONB. The one big use of JSON as opposed to JSONB is if you're just logging the JSON, but not really processing it. You're using it to log API calls, for example, or for forensic purposes. You want to make sure you have exactly the text that came in from the web. JSON is probably the right thing to do because it's faster to insert. And it also won't lose data by reordering the keys and doing things like that. Basically, for anything else, use JSONB. Unlike JSON, you can index JSONB in useful ways, which is very handy. And the built-in JSONB field type uses JSONB, so just roll with that. JSONB has GIN indexing, supports that set of operators, which are membership, key, has key, has all keys, has any key. And again, all of these work on the top level of the object. They don't look inside nested objects in the JSON structure. You can query paths, but the paths have to be rooted at the top level. Right now, there's no index-accelerated way of saying, find me a JSON object which has the key Fred at any level in the JSON structure. You can do it by just searching every record, but not using an index. So why would you use JSON in a relational database? Well, you're logging JSON data. One really nice use of JSON is you can create an audit table that works across multiple schemas. Audit tables have always had this problem in relational databases that if you have multiple tables all feeding into it, what schema does that singleton table have? And now the answer is it doesn't need a schema. You just use a JSON blob. You can pickle JSON objects if you're storing pickled JSON objects directly in the database. A feature of dubious value, but you can do it. And it's much nicer than using any of the other pickling methods, and probably a lot safer. Certainly a lot safer than YAML or something. And same things that we did with hstore. User-defined attributes or rare fields. We get admin widgets to go with a lot of these good types. The hstore and JSON widgets are really only good for debugging because how many people sit down and type in JSON into an admin form? Not really a good user interface. Okay, so that's what you get right now. If you say pip install Django and it gives you 1.9. 1.10, which is currently in alpha, has an interface to Postgres' full text search capability that's really kind of cool. Postgres has had integrated full text search for a long time, but in Django, you had to use Haystack or something like that to integrate with it, and it was all very complicated, and people just didn't use it, which is a shame because it's very nice. Django 1.10 has direct support for it, but first let's talk a little bit about the concepts. Full text search in Postgres is a pretty big ball of something, so there's a lot to know about it. So I'm going to try and simplify it a bit. There's a basic type in Postgres called a TS vector, which is a block of text. It's the thing you're going to search, like your blog entry, a journal article, description of an item, that's been encoded for full text search. So you can store it in the database, you can create it on the fly. It's a built-in Postgres type. There's a process that when you turn a text into a TS vector, it requires this thing called a configuration, which is a package of things like which language it's in, which stemmer to use, what rules to take to strip plurals off of the word and things like that. There's this big, and all of that stuff is wrapped together in Postgres. It's called a configuration. Postgres ships with a bunch of built-in configurations, which is good because it's totally a pain in the neck to create a new one. So generally just use those. Generally, for example, if you're searching text in English, you're going to be using the English configuration, and you don't have to worry about any of this stuff. It just all works for you by magic, which is nice. There's a function in Postgres called toTsVector that you drop the text into and a TS vector flies out. And it looks kind of like that, my big text field, English, bah. Django calls this under the hood for you in most situations in the new stuff, which is really nice, so you don't have to sit down and write a big PGSQL function or something like that. The basic thing we get with the new full-text search functionality is this operator for query sets called search. It calls toTsVector for you. Unfortunately, without any indexing, it does do a sequential scan. It picks up each record, takes that field, turns it to a TS vector, applies the full-text search operator, and returns it. And as you can imagine, this is not super fast. It looks something like this. For the field body text, do a search, and a full-text search of everything that has the word cheese in it. This is from the docs. We can, however, manipulate these directly in Django now. There's a type called search vector, which is a Python version of a TS vector. What's nice about these is it lets you search more than one field at a time because you can take two TS vectors and slam them together. So if you're searching the article title and its body, for example, you can combine those into one. All of that stuff, though, happens while the query runs, which can be pretty expensive. So the other side, the query text, sort of conceptually like a query set for full-text search inside of Postgres, is this TS_query object. It translates words into queries using stemming and things like that. For example, and you can combine these using Boolean predicates. For example, find everything that contains potato in Ireland, or everything that contains potato or penguin. These are from the docs. I have no idea why they use these particular ones. But so you can build up your full-text search using these. You also can rank the results of the query. Specifically, the full-text search functionality in Postgres also produces a ranking of how strong the match is, which you can use the way you imagine full-text search working anywhere in the world to sort the results. So, order by descending rank. There's lots more good stuff here. For example, you can change the rank of how much each individual field contributes to the rank. For example, you might want the article title to weigh more heavily, or its keywords to weigh more heavily than the body. So you can do that stuff. And you can set different search configurations from Django. For example, if you're searching in French or German, you might want to set those. Okay, but all this stuff is still doing sequential searches unless you index. So you can create just a simple index using Gin on TS vectors. In fact, Gin was originally introduced to support full-text search by using the TS vector function, and that'll just magically cause that __ search operator to speed up. However, if you're really getting serious about full-text search, you want to do fancy indexing, like combining multiple fields with different weights. Like saying, I want to do full-text search, but I want the article title to weigh more heavily than the keywords, and the keywords to weigh more heavily than the body. But I only want to do a search across one search. I don't want the user to say, well, search the article title and now search the keywords, and that kind of thing, because that would be that is not the user interface people expect anymore for searching. What you can do is create a separate TS vector out of all the fields, and then store it as a separate as a column, and then search that column. Django now, as of 1.10, provides a search vector field just for that purpose. So the question is, how do we keep this thing up to date? Well, we can do it in the app, like update it on each model instance change, override, save, and update it that way. Or you can use a trigger in Postgres. That's a better technique because it means if you come in, you do a bulk load or modify something directly in the database, the trigger will take care of updating this. The Postgres docs actually go into a considerable amount of detail on how to write that trigger. So you can look there. Then lastly, there's kind of little bits and bobs. Postgres, there's some new Postgres-specific aggregation functions like string_ag, so you can check that out. Postgres, the now function in Postgres stays constant within a transaction. So if you call it 3 times in the same transaction, you get the same time value back, which is actually quite useful if you're timestamping a bunch of records. And there's now a transaction now function in Django that has the same behavior. And there's an unaccent filtering. You can just read about that in the documentation. And that's everything. Questions?
If anyone has any questions, come here to the mic here so we can have your question for the recording.
My app is still using the old Django tagging for things. Would the array thing essentially make that pointless? I mean, could you just store a comma-separated list of tags and it just works out of the box?
Well, I would certainly, if I were designing a new application right now and I was doing tagging, I would definitely do it as an array, for sure, because that's a very obvious, nice use of tagging. Obviously, if you're you have to evaluate for yourself how much pain you're willing, blood you're willing to shed to do the conversion.
As long as it's easier than generic foreign keys.
Yeah. Boo hiss generic foreign keys, but anyway.
Sorry, I know the JSONB is only available in 9.4, in Postgres 9.4. What about the other features like ranges and stuff like that?
Ranges came in, I want to say 9.2, but they've been around for a while. And JSON, JSON came in 9.3 and JSONB in 9.4. So, just remember 9.1 goes end of life in September of this year, and 9.2 goes end of life in September of next year. So come up with an upgrade plan if you're earlier than 9.3.
Hi, thank you very much for this. This was very informative.
Great.
You mentioned while discussing hstore that it was going to incur an extra query during the standard way of handling it in Django, and that you sort of hinted at the fact that we shouldn't be doing it that way.
Specifically, if you're using, you can set a max connection age in Django since 9, anyone remember, 6, 7? That Django itself will reuse connection so it doesn't connect on every web cycle. So do that. That's a significant performance enhancement in Django. If or if you're using something like PG Bouncer that keeps connections open and pooling in session mode or something like that. It's not a big deal, but it's worth noting because Django already is pretty chatty on the wire. Things like the time zone and this and that, and transaction isolation mode. So, it's kind of embarrassing to see begin 23 different things and then the one query it was connected to put in. So, so having that kind of connection persistence is very valuable.
Thank you.
If you go back a few slides, I'm trying to understand why you would recommend to build a new basically column and using triggers and so on. Why would we use, exactly here. Why can't we, for example, use a functional index? So an index that would be based on a function that would basically...
You could. The biggest problem there is you have to send in you have to use exactly that expression every time you do the query. And if you don't use exactly that same expression, Postgres won't use the index because it doesn't match up doesn't match it up. So the advantage here of doing it this way is that you can control the upside is you can just query that one field easily using whatever query predicate you want. The downside is you have to it goes through the overhead of maintaining it and the space to store it, and it's not free. You create the index on the search vector field rather than on the individual text fields that you're doing, and you have to go through this kind of jump through the flaming hoop of creating the trigger, that sort of thing.
So there's no plan in Django. It would be nicer if we get both, the best of both worlds, which would be Django would be able to generate the right query.
I would use this specifically if I'm using Django because if I'm using an ORM, I can't guarantee I'm always going to be writing the query that will end up in Postgres will be exactly in the right form that it'll match the expression index.
Okay. Thank you.
Yeah.
Any more questions? No? Let's give our speaker a round of applause. It's break now. It's happening in the expo hall. There should be coffee and tea and maybe snacks. I'm not sure.
Very sure.
The next sessions will start on
and
time. So
if you're-
in this
yeah,
room, the next talk will start at 4:30. See you all.